The value change dump or VCD file is usually generated in a human-readable ASCII format after running the logic simulation of the digital design with the test bench in any simulation EDA tool. Initially, the VCD only stored the signal transition value, but it was later improved to include both the signal strength and direction. The signals are represented in the logic hierarchy with scope declarations. The VCD file is compact and efficient. It contains information such as signal transitions, duty cycle, and the observation window. VCD is supported by most logic simulators and waveform viewers. The VCD file records simulation activity, so it is mainly used for precise dynamic and static power calculations. An example of a sample value change dump or VCD file is provided here. The header section includes the date, simulation information such as the tool name with its version used to generate the VCD file during simulation, and the timescale with a value. Here it is in nanoseconds. The next section is a variable section that displays the top of the design, signal names, and scopes. In this VCD file, there are 4 signals: clock, A, B, and Y. The $var declaration now includes the direction of the signals, such as input, output, in-out, wire, and reg. The strength of the signal, which is represented as a pair like strong 1, strong 0, or weak 1, weak 0. Here, you can see that the signal clock is a wire with a 1-bit size, represented by the identifier code symbol. The identifier is essentially a single special character symbol without a space used to denote a signal in the VCD. The initial states of the signals are defined here, and all the signals are initialized to 0. The values change section is shown below. It displays how signal values change over time during the simulation. The dump vars command is used to record these value changes. The simulation starts at 0 nanoseconds, which is indicated here by the hash, followed by the time value. All timestamps are measured in nanoseconds. At 5 nanosecond, the clock is high. At 10 nanosecond, it is low or 0. And again, at 15 nanosecond, the clock is high. This shows that the clock signal first rises, then falls, and then rises again. Therefore, the clock changes periodically every 5 nanosecond. The duty cycle isn't directly stored in the VCD file. It can be calculated using the high time and the period. Here, the clock changes every 5 nanosecond, and the total period is 10 nanosecond, so the duty cycle of the clock is determined to be 50%. The observation window is determined by the timestamps in the VCD file. The first and last timestamps indicate the start and end points. Here, it begins at 0 and ends at 100. This information from the VCD file will aid in calculating the design's power.